Hello there today. This is Mr. Vessel here, and I'd like to take today's video to look at the 2018 number 1 from the AP Stats exam, and what the theme of this question is bivariate data. So basically what I wanted to talk about is some strategies when you run across these kind of questions, and some common themes that you might notice with this type of question. So let's dive in here, and what this one is going to investigate is a random sample of 11 customers and checking the relationship between the number of customers in a checkout line and the time it took to finish the checkout. And as soon as the customer entered the line, data were collected on the number of customers who were in line in the front of the selected customer and the time in seconds until this selected customer was finished with the checkout. And the data shown below in the following scatter plot, along with a corresponding least squares regression line and computer printout. So often in an AP Stats question, you're going to see this computer printout, and really once you kind of make sense of this printout, a lot of these questions aren't too difficult. And let's take a look here. So one thing that you might look at first is just this general shape of the data sets here, and then we've got a line here, but you'll always notice, like with an AP Stats display, it will have the variables labeled on the axis. We got the customers in line here. That's why you'll notice like dots that are obviously integers, and then in the time in seconds you'll see those two. And then this dot right here kind of stands out, where at 3 customers in line, it was a really fast time compared to some of the other ones. It's just something that as we glance at the data, we'll notice. And then down here we get this actual printout. A lot of the numbers in here are actually not that relevant. A couple of them that are really important, you'll always have the coefficient column, and the coefficient column is the one that you can use to build the regression equation. In this case, the constant, you'll always see a phrase here about constant, and this number, this is our y-intercept. And then we get this other number down here, this 174.4, this is our slope. And what will always be the case too with these labels, you see this customer's line, it is the x variable in this case. So there's always an indication of somehow that you get this, and that's not always the exact same phrasing, but you'll see a description that maybe the x variable or the customer's in line in this case. And what you can use with this is you can actually just build the equation from this information. And in this case, I'll draw that out here. We have a time, and again the equation is always a predicted value, so our predicted time is going to be based off of the 72.95, which is our intercept, plus the 174.40 times the number of customers. And in this case, we haven't looked at the tasks yet, but we might use this equation, we might not. But these two numbers are really helpful in building this equation. And the first task is actually just identify and interpret in context. There's always going to be a context with these. The estimate of the intercept. And in this case, we already have this number. It's this value here. So we just want to be able to interpret it in context. And what an intercept always is in context is when you have 0 things of the x, and it gives us a predicted value for the y. So in this case, the context is about number of customers in line, and what we're going to predict is the time in seconds. So we just want to indicate that and how the 72.95 relates. So something like this would be good. The intercept is 72.95, which means if there are 0 customers in line, we predict the time to check out is 72.95 seconds. And always we want to keep it in context, so we ought to make sure we mention the time that's measured in seconds here. We got the 0 customers in line, and it's another thing that's really, really important about answering this task. It's not that we know the answer is going to be 72.95 seconds, it's that we predict or expect the time to be 72.95. So that's a really important word that you have to mention when you're interpreting a least squares regression equation. That thing predicts for you. It doesn't tell you what's going to happen. And that's it for part A. Sometimes you're asked questions about slope, sometimes intercept, sometimes both. In this case, just focusing on the intercept piece. And then the second part there is identifying and interpreting in context what r squared is. And usually you'll get either r or r squared in this computer printout as well. Here's the r squared value in this case. And sometimes this number is given to the r squared adjusted, and sometimes it's not. You never need it. It's something you can just ignore, actually. You'll just interpret the r squared value here. So what r squared tells you is that how much of the variability in the time can be explained by the number of people in line. So what I'd like to think about it is that, well, it says identify it first. So r squared is 0.7333. And what that means in this case we can say 73.33% of the variability and the time it takes to check out can be explained by the number of people in line. So there are other factors that might adjust how long it takes for a person to check out, but 73.33% of how much the time varies is based off of the number of people in line. So a large portion of what we're going to use to predict how long it takes out is based on the number of people in line. And in general, that's what r squared always tells us, is like how much of the variability in the y variable could be explained by what we're measuring for the x variable. So in this case, it's really just knowing where to read that number and then how to turn that into a context in this situation. And then the last part is really just identifying what an outlier is. So it says one of the data points was determined to be an outlier, and circle it, and then explain why it's an outlier. So the thing that about bivariate data with outliers, sometimes it can be confusing, is, and I don't think this one's very difficult to find the outlier, but maybe explaining why it's an outlier is really important. So you'll notice this dot here that's pretty far below the line, and that's what makes this an outlier. Outliers are measured by the distance from the dot to the line. So when that gap is really big, it's always this vertical gap. This is a residual. It's not from dot to dot, it's kind of hard to tell. I'm going from this dot to this line, and the residual, if those are large, make outliers. So in this case, that's what we want to describe. So the data point, I can estimate what this number is. You can sort of tell it was a really, really short time. It's definitely, I mean, maybe about a minute or so. So let's just estimate this at 60-ish. So the data point 360 appears to be an outlier. And the reason it's an outlier is because it is well below what would be predicted from the equation. Because the observed time is well below the predicted time for 3 people in line. And again, really the big thing that is important about outliers is they're different than influential points. A lot of times it doesn't show up in this particular task, but there are definitely other data sets where you might see a dot way out here, and it doesn't necessarily mean it's an outlier. It could be an outlier just in the number of customers in line. It could be an outlier for the number of time it takes to check out. But if it fits the line pretty well, then it's not an outlier. Those are called influential points. So in this case, I don't think it's too tempting to circle another dot in this case, but it often can be confused, the difference between an outlier, which is a large residual, versus something that's influential, which is just something that could be extreme in both directions, like a dot perhaps way up here. So in this case, that's not too tempting, but we want to circle this dot down here and describe the fact that it's got a large residual. That's what makes it an outlier. And that's the 2018 number 1. I hope this was informative and helpful, and comment below if you have any thoughts or questions. Thanks for your time.